So we talked about binary systems, or binary system and decimal system. Now we're gonna introduce to you another, or revise another system that is very useful as well, which is the hexadecimal system. Okay, so the book talks about hexadecimal and octal. We're gonna cover in the lecture here only the hexadecimal, but you have to study by yourself the octal system. It's basically, same stuff as hexadecimal. Okay, so what is hexadecimal numbers? So hexadecimal is the base here is another system like the decimal and the binary, but the base here is 16. So in the hexadecimal number, the base is 16. So basically we have 16 symbols to represent the numbers. Okay, so let's see what are these symbols. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, these are all the numbers that we know, borrowed from the decimal system, which has only 10 symbols from 0 to 9. So basically here we need more, right? We need another, symbols until we reach 15. So we're gonna borrow something from somewhere else. So, they agree on using the alphabet. So A to represent 10, B for 11, C for 12, D for 13, E for 14, and F for 15. Okay, so we're gonna construct any number based on these 16 symbols. Okay, so for example, let's now see how we translate something from hexadecimal to decimal, something that we people understand very well. Okay, so let's take an example like 2, 3, 4 hexadecimal. So this number is written in hexadecimal. It's not 234. It's something else that we're gonna do now. We're gonna convert it to decimal so we can understand, in a very easy way what this number is actually represent. Okay, so what we do. So this is actually equal to 2 multiplied by the base, just like what we did with decimal and binary, 16 to the power what? 0, 1, 2, plus 3 multiplied by 16 to the power of 1, plus 4 multiplied by 16 to the power of 0. Good. Let's continue. So 16 square is actually 256. So this is 2 multiplied by 256 plus 3 multiplied by 16 plus 4, because 16 to the power 0 is just 1. Okay, so this is actually equal to, if we calculate this add up to 564 with base 10. So it's completely different. Okay, it's not 234, as I say, it's 564. Okay. Now we have the question, why we need such representation? Okay, let's do now the conversion from hexadecimal to binary. Okay, so what we do here is a very simple stuff. To convert it from hexadecimal to binary, it's really simple. Okay, so you just take each digit and convert it into a 4 binary. It's binary number. Okay, so what's 4? I mean, how we convert 4 into binary? 4 is actually 0, 0. I'm sorry, not 0, 0. It's 0, 1, 0, 0. I mean, we convert each digit into a 4-bit or 4-digit binary number. So 4 is actually 0010. You may say this 0 here at the end has no value. It has no value for the 4 only, but for the conversion, it has a value, as we will see now. Okay, 3 is 1100. So this is a conversion of 4. This is a conversion of 3. And 2 is 0100. This is basically the representation of this number in hexadecimal 234 into binary system, which is very easy. So now we start to catch up why we need this hexadecimal. Okay, basically the compactness, because binary system or binary numbers, which we need, unfortunately, to deal with computers, okay, has only 2 symbols to represent the numbers, 0 and 1. Then usually the numbers get bigger when we represent them using binary numbers. So for example, 546, which is only 3 digits, very compact, is converted to 10 digits. Let's ignore these last 2 zeros. These are 10 digits. It's still big, even after neglecting the last 2 zeros. This is 10 digits, from 3 to 10, more than 3 times. Okay? So, hexadecimal and the decimal are compact form of binary. But hexadecimal has one extra advantage. It's very easy to convert a hexadecimal number to binary and vice versa. So again, if you want to convert a binary number to hexadecimal, you just divide it into 4s, then convert each digit, each 4 bits to its representing digits in hexadecimal. Then you will have the hexadecimal number. And remember, each one of these symbols from 0 to 1 until F needs 4 binary digit number to represent it. For example, 0 can be written as 0000 in binary, of course. And 15 is 1111, which is the maximum number. So we don't need more than 4 bits to represent any symbol of the hexadecimal symbols. Okay, from 0 to 15. Now, let's take example for this, for converting from hexadecimal to from binary to hexadecimal. Let's take, for example, this number here, 1111, 0000, 0101, and 1101. Okay, this is in here. It's converted this to hexadecimal. Again, I just divided them for you. So these 4 digits, let's begin from here, that's fine. So this is 15. 15 is F. Don't write 15. 15 is F. Okay, these are just 0. This is 1 plus 4, which is 5. And this is 8 to the power 2 to the power 0, which is 1. 2 to the power 1. This is 2 to the power 3, which is 8. 8 plus 4, which is 12. 12 plus 1 is 13, which is D. D is 13, which is 1011. Okay? So it's very easy to convert from binary to hexadecimal and vice versa. And it's very compact. So here you have 16 digits. Here we have 4 digits. 1 to 4. Okay? So it's compact, at the same time easy to to convert from hexadecimal to binary and vice versa. So again, why we need it? Give me some application in which we really need hexadecimal numbers. And the application is memories, something that you're gonna implement in this course using VHDL. So in memories, we need an address for each location in the memory. Let's give, very simple examples. Let's say you have, very simple memories that only have two locations. Okay, two locations, only two locations. A memory in some dumb computer, that have only two locations. So we need an address for each location, a unique name, let's say so. So we just need one bit. So this address here is 0 and the address here is 1. How about if we have 4 locations? Can we use still one bit? No, because if I call this 0 and if I call this 1, how I can call this 0, how I can call the third and fourth place? If I call them 0 and 1 again, if I want the value in location 0, should you give me this one or this one? If I want the value in location 1, should I use this one or this one? So we need another bit. So 0 1 0 0 0 1 1 0 1 1, right? So basically we need log 2, log to the base 2, the number of locations. So here log to the base 2 of 2 locations is actually 1 bit. Here is log 2, so the number of locations, which is 4, which is 2 to the power of 2. So this will give us 2 bits. Good. And here is the addresses. Still no problem. But how about if you have, so here is 2 locations. Here is 4 locations. Now, how about if you have 4K locations? 4K locations. And 4K is not 4,000. Okay, in binary, 4K is different. It's approximately 4,000, but let's see how. So on a side here, 1K first in binary is actually 2 to the power 10, which is 1024. If we convert 2 to the power 10, which is a binary number, to decimal, it will be 1024. Okay, 2 to the power 11 is actually multiplying this by 2. Okay, because 2 to the power 11 is actually 2 to the power 10 multiplied by 2. So this will give us 2048. This is 2K. How about if we multiply 2 to the power 11 by 2? It will give us 2 to the power 12. And this is 4096. This is 4K. Okay, so we have 4096 locations. Of course, I cannot draw all of them, but you imagine that we have 4,000 locations, 4,096 locations now. And we need a unique address, a unique name, a unique symbol to represent each one of these locations. So we again go to our magic here formula, log 2 4096, which is log 2 to the power 12. So we need 12 bits. So this guy here will be 0 0 0 0 0 0 0 0 0 0 0 0, 12 bits. If we convert this number to decimal, it's just 0. And you just continue. For example, the second location here is 1 0 0 0 0 0 0 0 0 0 0 0. And this is just 1. Then 2 0 1 0 0. And you continue here in the same stuff until you reach the final location, which is all ones. 1 1 1 1 1 1 1 1 1 1 1 1. And if we convert this to decimal, it will be 4095. not 96, 4095. Because we start from 0. Okay. Like here, for example, we started from 0. This is not 4. We have 4 locations. So this is 0, 1, 2, 3. Okay. Here we have 2 locations. So we started from 0 to 1, not 4 to 2. Good. So basically in memories, we need a very big, binary numbers to represent each location. Here I'm talking about 4,000 locations. Just imagine your cache in your computer is 4 mega, or the RAM in your computer it's in gigas, right? So basically dealing with such massive numbers, binary numbers, is really bad. But and again, if we convert them to decimal, they will be compact, okay? But it's hard to convert from binary to decimal and from decimal to binary. But with hexadecimal, you can do that in a very easy way. So let's have an example. So this is 15, which is F, 15, which is F, 15, which is F. So the address of this location can be just represented as 3 Fs like this. This location here can be, converted like this. And this is 0, 0, 2, and so on. Very easy. Just divide them in 2 chunks. Each chunk is a 4-bit. Then convert each 4-bit alone to its hexadecimal representation, which it would be something from 0 to F. Okay? So that's why we need hexadecimal, because we can easily refer to addresses in the memory in a very easy way. Okay? So let's conclude until that point in that lecture, and we can continue our revision in our third video.